Good day, welcome back to part 2 of our discussion on differentiating trig functions. And in this video we will come up with differentiation formulas for all 6 of the trig functions. Now, in order to proceed, we noted in our previous video that we need a differentiation formula for sine and cosine. And the only way we can come up with such a formula is to go back to the definition of the derivative. And when we write out the definition of the derivative, we have that f prime of x is equal to the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x all over h. And then we put things in terms of the specific function we are interested in. F of something is sine of something. So this would be f of x plus h for that composition, trying to make this as easy as possible. And we would have the limit as h approaches 0 of sine of x plus h minus sine of x all divided by h. And as usual, we cannot simply substitute in h equals 0. That would cause us to divide by 0. And the only possible way I could see to hopefully simplify this is to somehow rewrite this sine of x plus h term in the top. And the only trig identity that we might be able to think of or recall that would help us would be the sum formula for sine. That is the formula for sine of x plus y. And this would be equal to the sine of x cosine y plus cosine x sine y. And do not worry, this isn't a formula that we typically just remember off the top of our head, but what I'll note is that there is maybe a familiar version of this that we see. Sine of 2x is 2 sine x cosine x. And that's just the scenario when y in this above formula is equal to x. So that's a familiar occurrence of the sum formula for sine. And now that we've recalled this important formula, we will use it to rewrite the sine of x plus h so that we can have the derivative of sine of x. So in order to do this, we need to let each of those y's become an h. So just working from left to right, we would have sine of x cosine of h plus cosine x sine of h. And we are subtracting away sine of x, and everything is divided by h. Now becomes maybe the more challenging part, in the sense that we somehow have to evaluate this limit using previous limit laws, properties, or maybe a few important limits that we introduced in the previous video. So transitioning back to the top here, note that we saw in the previous video that the limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of cosine minus 1 over x is equal to 0. And what I'm going to now try to do is to get these two limits to somehow fall out of our limit. And the observation that I'm going to make, at least to get us going, is that in the top we have two terms involving sine of x. So I'm going to go ahead and just group those terms together and see what that leaves us with. And those two terms involving sine x, if we pull it out, we would then have a cosine h and a minus 1 divided by h. And then on the top we still have this plus cosine x sine h. And that's all over h. And I'm going to go ahead right now and just immediately break that up into two fractions. So that is to say, let's go ahead and just erase a little bit of this And note if we're going to break this up into two fractions, both of them are going to have that common denominator of h, and we're going to be adding them together. And then we can go ahead and use limit laws. And our limit laws tells us that we can break this up into the limit of the first times the limit of the second. And I'm going to go ahead and just note right now, when we take the limit of that first part, sine of x is a constant with respect to h. So that sine can be pulled in front of the limit. Similarly, with the second part, you'll have that cosine x that can be pulled out in front of the limit. So we would have the limit as h approaches 0 of sine x, and I'm just getting it ready for that step we were alluding to, plus the limit as h approaches 0 of cosine x times sine h over h. So in the first limit, as indicated, sine x is a constant, which can be pulled out front. In the second limit, cosine is a constant, which can be pulled out front. So this would be sine of x times the limit as h approaches 0 of cosine h minus 1 over h, which should look familiar, plus cosine x times the limit as h approaches 0 of sine h over h, which also should look familiar. So comparing to our formulas above, we see that the limit as h approaches 0 of cosine h minus 1 over h is that second bulleted limit, because remember, the variable or the symbol that we use, x versus h, is irrelevant. And similarly, the second limit is the first bulleted one that we see above. And now we are done. So we end up with, in this case, sine of x times 0 plus cosine of x times 1. And this is simply just cosine of x. And let me remind you kind of in summary here what it is that we have just calculated. We have determined that the derivative of sine of x is equal to cosine of x, which is exactly what we guessed in our previous video when we explored this graphically. And I also want to emphasize that there is a lot going on with this computation, and there are certain times when we will go through the details to show why a formula is true, as we've done here, and then there'll be other times where we will not go through the details. But this involves a lot of nice ideas related to the definition of the derivative, some trig identities, properties of limits, etc. So I thought it was worth going through and seeing a few of those details. So let's do it again for cosine. And I was just kidding about going through all of those computations again. Instead, what I'm going to note is if you do similar work, and I'll leave the details to you, you should be able to follow our argument. You'll find that the derivative of cosine is equal to minus sine. Now that we know the derivative of sine and cosine, so just to remind you, on the previous page, the derivative of sine is cosine, and we're indicating without work, but hopefully you'll take our word for it, the derivative of cosine is minus sine. With those two formulas in mind, we should be able to differentiate all of the remaining four trig functions by simply utilizing the quotient rule. So let's kind of work through this together with tangent, and then I'll let you practice with cosecant. If I want to differentiate tangent, the key is I cannot do it directly in its current form, but tangent is simply sine over cosine. And sine over cosine is something that we can differentiate quite efficiently using the quotient rule. And the quotient rule tells us low d high minus high d low all over that bottom squared. In substituting in our differentiation formulas, we know that the derivative of sine is cosine, and the derivative of cosine is minus sine. So working our way from left to right, we have cosine times cosine, and then we are subtracting away sine times the derivative of cosine, which is a minus sine. And then this is all over cosine squared. So note immediately here, the minus a minus becomes a plus. And in the top, we have cosine squared plus sine squared, all divided by cosine squared. And if we were simply looking for the derivative, we would stop. But what I want to do is come up with the most convenient way of writing this derivative so that we hopefully have a formula that we can easily remember so that we can utilize it over and over again. And note, cosine squared plus sine squared is 1. And 1 over cosine is secant. So this is secant squared of x. And just to summarize a bit, we've noted that using the common formulas, the derivative of sine is cosine, and the derivative of cosine is minus sine, we can then use the quotient rule to differentiate the remaining 4 trig functions. And we just worked out the details for tangent. The derivative of tangent is secant squared. What I would like you all to do is to pause the video for a moment and use the quotient rule to differentiate cosecant of x, and just try to simplify it down to whatever you think is the most convenient possible formula. And then when we work through it together, we'll see if we agree or not. So hopefully you paused the video and you took a few minutes to work through this derivative. If we want to utilize the quotient rule, we need to rewrite cosecant as 1 over sine. Then applying the quotient rule, we think in words, low d high minus high d low, all divided by low squared. And the derivatives here work out quite nice. The derivative of a constant is always 0, so the first part just completely vanishes, and the derivative of sine is cosine. So that is to say we have minus cosine in the top, all divided by sine squared, which most certainly represents the derivative of cosecant, but I'm going to rewrite this ever so slightly just to hopefully have a convenient formula to remember. So I'm going to pull out the cosine over sine, which leaves a 1 over sine. So just trying to write this in terms of 2 familiar trig functions, we have minus cotangent cosecant. And typically when it comes to remembering the derivative of cosecant, I will almost always write this as minus cosecant cotangent. And I'm not going to go through the details here using the quotient rule to differentiate secant and cotangent, but you certainly could, and the derivative of secant is secant tangent, and the derivative of cotangent is minus cosecant squared. And I just want to make a couple quick observations, and one of them is that we now have the 6 trig functions all differentiated. So these are now 6 common formulas that we should be aware of. And a question students will typically ask is, oh, so that means I need to memorize them. And my response is always, no, you don't need to memorize them, but you certainly should know them. And note there's a difference there. When I say we should know them, that's because we've practiced using them, we've worked through a bunch of examples, and they almost just become second nature to us. Furthermore, I'll note that there's some symmetry to our formulas in a sense. The derivative of tangent is secant squared. The derivative of cotangent is minus cosecant squared. And then there's some similarity with the derivative of secant and cosecant. And a very common mistake or a common issue is not being able to remember where the negative signs go. Note there are 3 negative signs that appear in these differentiation formulas. And they appear only when you're differentiating one of the co-trig functions, cosine, cosecant, and cotangent. So for what it's worth, that is how I remember where the negative signs go. So just note a negative sign appears in the derivative only of the cofunctions. And by the cofunctions, I'm talking about cosine, cosecant, and cotangent. And that finishes our current discussion, but in our next video, we will immediately pick up and utilize these formulas to go through some common examples. So stay tuned and take care.